No, that says PC mute. Oh well, there you go. Right, my name's Jeff Gibson. I'm doing the part of the fabrication part of the course which deals with non-metallic materials, principally plastics and composites. And I have about 5 lectures. I apologise for last week's lecture being cancelled. Unfortunately, these lectures clash with another lecture course which I have, so I'm having to fit them all together. Were you told last week that my lecture was cancelled? Yes. That's good. Okay. Right, you've all got your diaries there. My next Friday's lecture is cancelled as well. Okay, so today is the 3rd of November. No lecture on the 10th. Somebody write it down so we all know. So I'll see you again on the 17th. Okay? So you can have an hour to drink coffee in a week's time. Right. I'm going to be talking about thermoplastic pipes. I know we get people from a whole range of different backgrounds, but we don't get many people who learn chemistry. Hands up who's done any form of chemistry. Yeah, that's chemistry. I did chemistry, yeah, okay. So that's a few, not too many. I have a specially simple version of chemistry, because if you want to understand thermoplastics, it's probably a good idea to have a little bit of knowledge about the chemistry of how they go together. You don't need to know too much. So I have my special simplified version of organic chemistry, which we call organic chemistry for dummies. Well, the other thing is I can't find a microphone here. Can you hear that?
Yeah.
So I presume it's being recorded by recap. Still haven't got the hang of recap. There's a red light on, which means it's probably working. Right. So this lecture is going to give you some information on the 3 most common thermoplastics for use in pipes. I'm talking about high quality pipes as well. I mean, there are low quality pipes for domestic use and things like that. But the 3 main ones are PE, which stands for polyethylene, PA11, which stands for polyamide 11 or nylon 11, and PVDF, which stands, as we shall see later, for polyvinylidene fluoride. So it's written down later in the course. All this stuff should be, have you looked on Blackboard for my part of the course yet? No?
Is there?
It's there?
Yeah.
Okay, so it's all there. Right, thank you. Right, so before we discuss these polymers and the manufacture of pipes, before we discuss these polymers and the properties, I'm going to talk about the manufacture of pipe systems and applications and joining techniques. So it's just the same stuff that you've had on steel pipes, except I'm giving it to you on thermoplastic pipes. But it's useful, as I just said, to have an appreciation of the chemical aspects of polymer behaviour. It's not necessary to take a full course in organic chemistry. Carbon forms covalent bonds. So here you've got a carbon atom. Each carbon atom forms 4 covalent bonds. Each bond actually is a shared pair of electrons with another atom. But actually, as an engineer, you can just regard a bond as being like a stick which joins the carbon atom to one of the other atoms. And this is one of the simplest molecules. This is methane, carbon with 4 hydrogens, CH4, and left to its own devices, the carbon atom will have these 4 bonds pointing towards the 4 corners of a tetrahedron. That's the way it prefers to be. So the molecule of methane is a tetrahedron, natural gas. And carbon forms covalent bonds with other elements, such as hydrogen, oxygen, and nitrogen. And each of these other elements has a number of bonds that it wants to have. In other words, it has a number of electrons that it wants to share. So I say covalent bonds are shared pair of electrons. Take some examples. Right, there's methane. The other elements that we need to know about for pipes are hydrogen, chlorine, fluorine, and hydrogen, chlorine, and fluorine all form one bond. So hydrogen gas, for instance, is H2, which is just 2 hydrogen molecules with one bond joining them together. Same with chlorine, one bond and fluorine. Oxygen forms two bonds, so oxygen wants to link to two things, and nitrogen actually wants to link to three things. So the oxygen that floats around in the air, O2, is actually two oxygen atoms joined by a double covalent bond. And the nitrogen that floats around in the air is two nitrogen atoms actually joined by three bonds, because nitrogen has three. So we'll see these examples in just a second. The carbon as an element is unusual because it can form long chain molecules by forming covalent bonds between carbon atoms and sometimes other elements. It's not the only element that does this, but it's the most important one. So polymers are long chain molecules consisting of many units. In fact, that's what polymer means. It's Greek. Poly means a lot of, and mer means units. So the chains are connected by covalent bonds, and this is a chemist, it's not a caterpillar, this is a chemist's drawing of the molecule of polyethylene. And in this molecule, the atoms are the correct sizes. They're the correct relative sizes. So the red ones are carbon atoms, and the green ones are hydrogen atoms. So that's what a molecule of PE looks like. And the thing about it is, if you get one of these molecules and pull it along its length, it's very stiff and very strong because it's connected together by covalent bonds. But all these atoms can rotate around each of these joints. So it's actually quite flexible. It's almost like a steel chain. Because a steel chain is completely flexible unless you pull it tight. And that's the same with these polymer molecules. And that has an important implication, because in the solid state, when all these molecules are packed together, the bonds between the molecules, most of the bonds holding together the solid, are not the bonds along the length of the chain. They're the bonds in between adjacent chains. And those bonds are weak bonds. They're van der Waals bonds, as we call them. And that's why thermoplastics, the weak bonds which join the chains laterally, they're what gives the material its mechanical properties. So that's why thermoplastics have a low Young's modulus, generally fairly low strength, and a low melting point. Of course, the advantage of the low melting point is that it makes them easy to form, because you can melt them, extrude them into pipe, and then cool them down again. Right, so there's the simplest example is polyethylene. Polyethylene is actually made from the gas ethylene. Ethylene is a byproduct of petroleum refining. You know, when crude oil comes out of the ground, there are all sorts of different fractions in it, and these fractions are never the ones you want, because the industry requires a certain amount of kerosene, a certain amount of petroleum, a certain amount of heavy oil, and you have to do chemical operations on oil to change the length of the chains after it's come out of the ground. And one of the things that's always left over, all the pieces that are left over after they finish doing that, is ethylene, this gas ethylene. So actually most of the polymers that we come across, most of the plastics that you come across in everyday life, are made one way or another from ethylene. Or the gas, everybody calls it ethylene. Actually about 40 years ago they changed the names of all the chemicals, and its proper chemical name is ethene, but everybody still calls it ethylene, because we're slow to catch on. And we have the difference between thermoplastics and thermosets. The thing about thermoplastic, which is what we're going to be talking about for most of these pipes, is that they're linear chains. There might be branches on the chains, but it's a linear chain, which means you can melt. Once you've melted it, the material will flow. So the covalent bonds within the chains, as I've said, van der Waals bonds between the chains, but they can be melted, they can be dissolved. Fabrication into pipes involves melting, shaping and cooling. And you can see just the way I've drawn this chain here. If you've got many of those together in a solid state and you apply a stress to it, the thing that you're mainly loading is the bonds between the chains, not the bonds within the chains. And the bonds between the chains are the weak bonds. You can actually make these polymers very strong. If you stretch all these chains out and line them all up, which is not easy to do, but if you do that, then you can make things which are things like Kevlar, which is very strong. It's stronger than aluminium or steel. Make bulletproof vests out of it. You can do the same thing with polythene, actually. It's called Spectra, but we don't use that in pipes. Right, that's thermoplastics. With thermosets, we actually have a network. It's different. You can't draw a network on a flat screen, but you imagine it's a three-dimensional network, and the network consists of chains of resin and cross-links, cross-linking the chain, so that when you make a thermosetting, when you make something from a thermosetting polymer, it actually involves carrying out a chemical reaction. And we're going to show you one example of that, which is the manufacture of glass fiber epoxy pipes. So the most important thermoset is epoxy resin. And that's a mixture. I'm sure you've all done things at home with epoxy resins where you get the two tubes and mix them together. Well, one of the tubes has got these, the green stuff in, and the other tubes has got the red stuff in. You mix them together, they react with each other, and they form this 3D network, which cannot subsequently be remelted or reshaped, so you can't recycle it. It cannot be dissolved in anything, and when you make something out of epoxy resin, the fabrication involves a chemical reaction, which is a little bit inconvenient. So those are two classes of materials that we're dealing with. Thermoplastic pipe materials, as I said, you start off with a monomer to make polythene. The monomer is ethylene. The polymerization reaction, you see ethylene has a double bond in it. You see this, my theory about carbon having to have 4 bonds. If you count the bonds here, there's 2 bonds with the hydrogen atoms, and there has to be 2 bonds between the carbons so that the carbon is happy and has 4 bonds. So the polymerization reaction breaks and opens up one of those bonds. So the bonds are at the end of the molecule, so they all join up together. So that's polymerization. And just one other example, I said most plastics come from ethylene. There's ethylene. You can change these hydrogen atoms on the ethylene for other atoms. For instance, if you take off one of these hydrogens and put on a chlorine, you get vinyl chloride, and you polymerize that, you get PVC. PVC is also used for pipes, as you probably know. So polythene is the most widely used thermoplastic for pipes. It's used for water, gas, oil, and actually for lining high-performance steel pipes. PVC has excellent chemical resistance, but it can be brittle. It's used mainly for water. In Holland they use PVC for gas for some reason, but most other places they use it only for water. And here's this other one. If you take off 2 of the hydrogens and put fluorine atoms on, you get vinylidene fluoride. And you polymerize that, you get polyvinylidene fluoride, which is CH2CF2. So PVDF's a little bit like polythene, except every other atom has fluorine on it instead of hydrogen, and actually that makes it very inert and very chemically resistant. So PVDF is used in the applications where you require the highest possible corrosion resistance and high temperature. So it's mainly used in oil and gas. It's mainly used as I say, for liners for steel pipes. So you have a steel pipe. If you want to use it to transport a corrosive fluid, then it becomes very difficult because the steel will corrode unless you use a special steel. I'm sure you're learning all about that in other parts of the course. One of the things you can do is you can take a carbon steel, which would generally be prone to corrosion, and you can put it in a thermoplastic liner, which means then you can transport anything inside the steel pipe. And one of the favourite materials to use as a liner is PVDF. And the other one is nylon 11. It's called nylon 11. There are many different types of nylons, and nylon is all called either polyamide or nylon. Polyamide is the chemical name. Nylon is the trade name. It's one of these names which have been so widely used that it's actually become the name of the material. It was invented by, nylon stands for the fact that these polymers were invented by DuPont of New York and London. So that's where the word nylon comes from. It has nothing whatsoever to do with the plastic material. And it's really called a polyamide. And this one that's used in pipes is interesting because there are actually 11 carbon atoms in there. And it looks very like, it's sort of 90% like polythene. It's mainly polythene, except you have this amide group. But this amide group has a very important effect, because when you have these chains lined up to each other, this group is polar and they stick to each other. So you have a lot of chains together in the polymer, the polyamide groups will stick to each other, and it has a fantastic effect. It raises the melting point by about 100 degrees C. Polythene melts at about 130 degrees C. Nylon 11 melts at about 230 degrees C. So it's a much higher melting point due to the presence of these amide linkages. Let me just see what I've actually said on this slide. The structure is like polyethylene, but it contains amide groups which are polar, and these raise the melting point, and they confer extra resistance to oil as well. So nylon 11. So in other words, your standard material, if you're working with oil, would be polyethylene. If you want to use it at a higher temperature, or if you've got a particularly problematic type of oil, you would go to either PVDF or nylon 11 for better performance. The other unusual thing about nylon 11 is it's not made from ethylene, as you can see. It's one of the few polymers at the moment that's made from a natural ingredient. Polyamide 11 is actually made from castor oil. So it's made from the original material is a vegetable oil, castor oil. Nylon 11 is strong and tough. It's used in liners. The problem is that this group, although it confers a high melting point, can also be attacked by water. So if you're using nylon 11 to transport oil field fluids, for instance, you have to be very careful about how much water is in there. You know water comes up with the oil, don't you? Have you done stuff about oil wells and things yet? Yes?
I mean, costs? No.
Yeah, but some of you understand it, and some of you don't. Yeah. But when you get oil out of when it comes up out of a well, it has water in it. Sometimes it has water in it naturally, but quite often it has water in it because you put in injection water. You have injection wells where you inject the water, which pushes the oil towards the wellhead. So the older the well is, the more water there is in the oil which comes up. And eventually, the thing that limits the lifetime of a well is when it starts producing so much water that it's not worthwhile operating. So oil-produced fluids contain some water. And if you're going to use it with nylon 11, there mustn't be more than 5% of water in it. Otherwise it will start attacking these bonds. And the trade name of this material, it's not usually called nylon 11, it's called Rilsan. Rilsan is the material that's used. R-I-L-S-A-N. Right. I have to mention PTFE, because you've all heard of PTFE, Teflon. The stuff, nothing sticks to it. Talk about the Teflon man, nothing sticks to it. It's very, very corrosion resistant material, nothing sticks to it. You can see it's made, once again, it's made from ethylene, but you have to replace all the carbons on the ethylene by fluorine atoms. And there's one problem with PTFE. It's a fantastic polymer. It would be great for making pipes. The problem with PTFE is that you can't easily melt it. It's a thermoplastic. Its melting point is about 330 degrees C, and the problem is its decomposition point is 300 degrees C. So you can't melt it. You can't put it into an extruder and melt it. So that's the reason why you don't see PTFE pipes. Actually, sometimes you see small PTFE pipes for medical uses, things like that. So PTFE is used in seals, it's used in sealing tape, all sorts of things like that. It can't be used in pipes because you can't process it. the usual method that's used for processing thermoplastics. Actually, for processing PTFE, you have to press it and sinter it. You take it comes as a powder, and you have to press it very hard together to form shape, and then you anneal the pressed product at a high temperature below the melting point. Keep it there for a long time, and the particles gradually stick together. It never melts. So that's why you don't see PTFE in pipes. And actually, some of the best materials that are used in pipes, like PVDF, are attempts to get to the structure of PTFE. So if you look at PVDF, it looks like it's 50% polythene and 50% PTFE. And this is processable by normal methods. So that's why it's used. And there are actually a number of other specialist polymers in this area which have fluorine atoms in. And the purpose of those is to enable them to get a very corrosion-resistant structure like PTFE. But PTFE, as I said, is used in seals, and it's also used in linings for valves. Right, so these are all the materials: polythene, polyamide 11 or Rilsan, PVDF. The other one I didn't mention is cross-linked polythene. I was talking about this difference between thermoplastics and thermosets. And a thermoset is a fully cross-linked network. You can take polyethylene and you can cross-link it a little bit, and that gives you actually huge improvements in its behavior. So the polythene that's used in liners is sometimes cross-linked, just very, very slightly. It means you can't use it again. It means you can't subsequently remelt the material and use something else. But it improves its temperature resistance by about 20 degrees C. So that's called PEX. If anybody mentions PEX, that's what PEX is. And it improves, I mentioned this thing called ESC, which stands for Environmental Stress Cracking. I'm going to talk about that later. But environmental stress cracking is a little bit like stress corrosion cracking in steels. It's a form of crack growth in the material which is induced. It's induced by the presence of various chemicals in the environment. Right. This is just a whole list of different polymers used in oil and gas, which you probably don't need to memorize. I mentioned PVC, which is quite important because it's used in water distribution, and in Holland it's used in for gas distribution. Polypropylene is a nice polymer, but it's not widely used for pipes. Polybutene 1 is used in the USA and some EU countries, but it's not widely enough used for us to talk about it in this course. And then there are two other polymers, fluorinated ethylene polymer and ethylene tetrafluoroethylene. And these are other mixtures of ethylene and PTFE. Again, trying to get this PTFE structure whilst retaining a processable thermoplastic. So you sometimes see these in the oil and gas industry. Right, here's the process. Anybody done plastics processing before? No, so all this is brand new. Thermoplastics, I said, they're long molecules. They have a high molecular weight, which means that the chains from which the molecules are made are very long. What this means, the implication of this, is that when you melt the material, the molten polymer has a very high viscosity. It has a viscosity. Molten polyethylene has properties rather like chewing gum. It's a very high viscosity liquid, you can't pour it. So if you wanted to make something into a final product, if you want to make a thermoplastic into a final product, you can't just, the melting and shaping process is actually quite complicated. You have to do some special things. I mean, you can imagine, for instance, stuff comes as granules of thermoplastic. You could try putting them in a beaker, and putting the beaker on a heater, on a hot plate or a Bunsen burner. I think that this might melt the polymer. In fact, it wouldn't. It would simply decompose some of the polymer, because one of the problems with thermoplastics is they have very low thermal conductivity. Like they have such low thermal conductivity that they're sometimes used for insulation. And the other thing is, even if you could get a beaker of the material and get it completely molten, how would you shape it? You couldn't pour it into a mold. You turn the beaker upside down and the material would not flow out because the viscosity is so high. So you need a special machine for making things out of polymer, and it looks like this, and it has a screw in it. It looks a little bit like a sort of mincing machine that you would see in a kitchen at home. It's an extruder, you have a screw, and the screw rotates. And you feed the granules in at the back end of the screw, and the extruder conveys the granules along this heated steel barrel. And whilst the granules are being conveyed, they're compressed and they're rubbed against the wall of this tube in the extruder. So you overcome the fact that the material has low thermal conductivity by pressing it against the hot steel wall of the extruder and rubbing it along the wall of the extruder. You can see, if you look at the dimensions of this screw, the root of the screw here is smaller than here. So as the material in powder form, in granule form, as the material is conveyed along the extruder by the screw, it's actually compressed and rubbed against the wall of the extruder. And so when we get to here, we have molten polymer. Now, almost every process that's used for making things out of plastic involves a machine like this, a machine with a screw which conveys and compresses and melts the material. Interesting thing about it, your barrel is heated to a temperature which is just a little bit above the melting point of the polymer. But where do you think the energy comes from when you melt the polymer?
The extruder effect as you rotate the screw on the extruder.
Say it a bit louder.
As you rotate the screw, the extruder,
Yeah.
it's pushed out. It pushes.
Yes, it pushes the material along the barrel. And where does most of the energy come from that melts the material? Does it come from conduction of heat into the material? I'm trying to get you to say the wrong thing. Because there are two sources of heat with this process. One is conduction of heat from the steel barrel into the polymer, and the other is the fact that you're doing work. You're doing a lot of mechanical work on the material. It's firstly rubbing it by friction against the wall of the barrel, and secondly, when the material is melted, the viscosity is very high. So when you make it flow, that dissipates energy and it gets hotter. And actually, with an extruder like this, most of the energy required to melt the material comes in not by conduction through the barrel, it comes in from the energy of the motor, which drives the screw. And in fact, with many extruders, you can actually, once the extruder's going, you can turn off the heating. And all of the necessary heat will be supplied by conversion of mechanical work into heating the material up. So the material is heated up, the air that was between the granules is squeezed out by squeezing the granules together. So here you have a homogeneous mass of polymer. Also it's mixed by shearing the material between the screw and the wall of the extruder. So the extruder is really, it's a machine for producing polymer melt at a consistent temperature and flow rate. And that's what you have here. And then depending on what you want to make, the rest of the downstream process looks, it may be one type of process or it may be another type of process. But if you want to make pipe, the process is very easy because you have to make it into the form of a tube. So the material is made into the form of a tube. So you have this is called a torpedo. So inside the barrel of the extruder, you have this torpedo, and the polymer flows around the outside of the torpedo to form a tube. And you probably ask, what is it that keeps the torpedo there? I haven't got a, can't see a pen, but the torpedo thing is actually held inside the barrel of the extruder. You can't see it the way I've drawn it, but it's actually held in probably 4 different places inside the barrel of the extruder. So the melt flows around it, and then it joins up and forms a pipe. So you have your melted thermoplastic comes out the end of the extruder in the shape of a pipe. And at this point it's a molten liquid, but the viscosity is so high that it will hang under its own weight. So it doesn't just dribble out the end of the extruder and fall on the floor, it carries on. Remember, when you're thinking about the properties of a polymer, I'll think about chewing gum. It's a liquid, but it has some high viscosity and it has mechanical strength. So here is the pipe, and it's then cooled and shaped. And this unit is called a vacuum calibrator. It's pulled to form the shape and to form the accurate shape. It's pulled inside a very accurate steel tube. And this steel tube has slots in the wall of the tube, and you apply a vacuum. So this calibrator unit contains steel tube with slots, and it sucks the thermoplastic pipe against the wall of the calibrator. Sorry, did you?
I said to itself.
Say it a bit louder.
To itself, to the wall of the calibrator.
Yes, it sucks it. Because so you have a vacuum here, so the tube is sucked against the wall of the calibrator, and it's held against the wall of the calibrator as it passes through the process, and it's cooled down at the same time. So that's one thing to remember. It's an important thing to remember about thermoplastic pipe, is that the accurate dimension of the thermoplastic pipe is the outer diameter. And that is because the outer diameter is formed by pulling it against these calibrators. The material actually contracts quite a lot. Polythene contracts by about 10% when you cool it from the melt down to room temperature. But you keep the diameter constant by sucking it against these calibrators. And the calibrators themselves are in a water bath. So the whole thing's underwater. There's water lubricating the interface between the pipe and the calibration unit. And actually I've only shown one water bath here. In a real extrusion process there might be 3 or 4 separate water baths to cool the material. And then at the end of the process you have a haul-off, which is just like a big caterpillar, and it has on it rubber pads so that it can grip the pipe without squashing it. And this is what makes the pipe pass through the process. And then at the end of the process you either have a saw and you cut the pipes into the length, usually 9 meters, usually the length of a truck, because you wouldn't want to make them any longer than that. If it's a smaller diameter pipe, sometimes it's rolled into a big coil. But more often than not, it's cut into lengths. And actually, after you've cut the pipe into lengths, sometimes you heat up one end and you do a forming operation, because sometimes you need a pipe with a socket in so you can join it to other pipes. But I'll talk about joining pipes in a minute. So that's the process, that's the extrusion process. I'd like you to be able to describe that. So in summary about extrusion, the polymer granules must be heated, melted, shaped and cooled to form the final product. And the process for doing this is governed by the fact that thermoplastics have low thermal conductivity and when molten a high viscosity. So that's the process. Just bear in mind that the actual process is a lot longer than I have drawn it, because the cooling of the material is quite slow. It might take a couple of minutes for the material to cool down from the melting point down to the temperature in the pipe. So it's not unusual for one of these production lines to be 100 meters long. So you'll visit a thermoplastic pipe factory. You see that they have these long lines which are about 100 meters long. They're usually several calibration units, usually followed by several water baths where water is sprayed onto the material. Yes, sorry, did someone have their hand up?
Oh yeah, sorry. It was just about you were saying about the accurate dimension,
Yeah.
the diameter is the outer diameter.
Yeah.
Are the sizes different to the MPS ones for steel, and do you always go for the outer diameter?
I don't know which diameter you go for with steel.
Because it usually changes from when it gets past about you're basing it on the the outer diameter
Okay.
out of 12 or the inner diameter
Right, well,
of 12.
Any thermoplastic pipe that you buy,
Yeah.
you will specify the outer diameter and the ratio of the wall thickness to the diameter. You can actually make pipe with an accurate inside diameter, but hardly ever done. And the wall thickness of the pipe is determined by the ratio of the speed of the haul off to the speed of the extruder. So if you run the haul off faster, you'll get a thinner wall. If you run it slower, you'll get a thicker wall. And there's usually some sort of measurement device here, because all of these factory processes now have full closed loop control. There's usually some measurement device like an electron beam or something like that, measuring the wall thickness of the pipe as it comes out of the process, and then feeding back the information to the speed of the haul off.
Excuse me. You're saying that a lot of the energy is transferred to the plastic through the motor and the gearbox.
Yeah.
The rotation. So what kind of speed are we looking at the extruder?
The screws running usually at about 100 and it's usually about 2 revolutions per second. Yeah. So it's 100, 120 RPM. So it's not really fast, but it's
sufficient.
It's fast-ish.
What kind of temperatures are we looking at?
Pardon?
What kind of temperatures? Are we
The
looking at?
temperature, usually the material comes out about 20 degrees C higher than the melting point. The melting point of polyethylene, I'm sure it's in the notes somewhere, but if you just want to write it down, the melting point of polyethylene is 130. The melting point of mal 11, I think, is 220. I might be wrong there. The melting point of PVDF is 185. So you get it up to a higher temperature. You don't want to get it just to its melting point because you need to heat it higher because you need to lower the viscosity of the material. Right. So if you go to a thermoplastic pipe factory, there'll be about 10 lines like this, all producing pipe. That's one of the things, you visit a pipe factory, all the lines are always in production. You never see a line unoccupied, you never see a line standing still, because the capital cost of one of these lines is probably about £1 million. So you don't want to have the thing standing still, not making any pipe. Right, again, that just shows, it's just a repeat. The extruder conveys the polymer granules along the heated barrel, melts them by friction, viscous heating and conduction. And the granules are compressed by the change, you see the change in the flight depth of the screw, and that eliminates the air, keeps the air back, and the thermoplastic melt passes through the die where it's formed into the shape of a tube. And obviously this thing that I've shown you at the end of the die can't just sit there in space. It's actually held there on in 4 different places, which I haven't shown. There's the calibrator. The melt passes from the die into the vacuum calibrators, which are in a water bath, so the whole thing's underwater. And the pipe is held by vacuum against the calibrator surface while being cooled, and this accurately controls the outer diameter. And there are usually several cooling zones like this because of the low thermal conductivity of the thermoplastic. So as I say, a line might typically be 100 meters long. There's the haul off. Beta ray gauge, that's an electron gauge. That just fires beta rays through the wall of the pipe, and the thicker the pipe wall is, the fewer beta rays you get. So it measures the wall thickness of the pipe and gives you feedback control to the speed of the haul off, so they gives you a constant wall thickness of the pipe. But that still means that the inner diameter is less well controlled than the outer diameter. So there's the process. And then finally, for socket and spigot joints, sometimes there's an additional thermoforming operation done on the end of the pipe. Right, and there are many different techniques for joining thermoplastic pipes, and these are the main ones. The cheapest, most effective is butt welding. That is, you just weld the 2 ends of the pipes together. I learnt everything that I know about joining pipes just from looking at holes in the ground. When you're walking through town, you see they've got the road dug up. Go and have a look and see what's in the hole. It'll be a pipe. And they'll have machines for welding the pipes together and things like that. It's a good way of learning what goes on. So that's the butt welding is the cheapest way of doing it and probably the most effective. I'll describe that in a minute. There's another process called electrofusion, where you actually have a fitting which you weld onto the pipe. I'll talk about that in a minute. The socket and spigot, like I showed you, that's like we have here. The thing about socket and spigot is that the socket just has a rubber O-ring seal, and you just push the pipe into it. So it doesn't resist the axial load on the pipe. So it's probably okay for a buried pipe. The pipe's going to be buried, socket and spigot joint is fine. But if you had it just lying on the surface, then it would move around and the pipe would open up. So it gives you no resistance to axial load. There are various mechanical joints represented by the box here. And there's, if you look at some of the things which are used in domestic pipes, mainly with PVC, you can do solvent welding. So you have a solvent-based cement. So you push, again you have a socket and spigot, and you push the spigot into the socket, but before you do that you coat it with the cement, which dissolves some of the thermoplastic components as well. Now that's quite an effective way of joining pipes, but it doesn't give you good mechanical properties. It's all right for drainage pipes, it's all right for the sort of pipes that you have coming out of your sink in the kitchen or something like that. But it doesn't resist high loads, it doesn't resist high pressure. Because if you think about it, you have a solvent in the cement which is used to glue the pipes together. You cannot achieve the full strength of the joint until that solvent is diffused out. And that takes a long time. So solvent welding, if you're working in the oil and gas industry, which most of you will be at some stage, you wouldn't use solvent welding. Right, so here's the first one. Here's butt fusion. So the butt fusion process is completely automated. You don't want anything to be dependent on the operator. So once you put your pipe in the butt fusion machine, everything is controlled. So you can't mess it up. So you clean the pipe, they cut the pipe, and you have a machine which shaves the ends of the pipe flat. So just before you're going to join the pipe, you have a machine with a blade which spins round, which shaves off a small amount from the end of the pipe, just in case that material might have been contaminated or dirty or something like that. The pipe is clamped. So the two ends of the pipe are clamped here and here. And you have a hot plate which you can put between the two lengths of the pipe, and you have a controller. So and everything is controlled by this controller. So the person doesn't do anything. All the person does is assemble the two lengths of the pipe, put them in the machine, and press the button. And then after that, the controller does everything. And you see these things. Again, look in the hole in the ground. You see these machines lying around there. And the advantage is that you don't need any type of fitting to do this. You can just straight away join two pipe ends. So it's the equivalent of welding a steel pipe. Well, it is welding. So what happens is the first thing you do, your hot plate is heated to a temperature above the melting point of the polymer. So the first thing that happens is that the pipe ends are pushed up against the hot plate at a known force, and they're kept there for a known period of time, which will melt a certain amount of the thermoplastic material. Then they're pulled apart, and the hot plate is pulled out. The hot plate is folded out, and then they're pushed together. Two pipe ends are pushed together, again with a very reproducible force, and you get a good weld. And you can see here that you get a bead, you get a weld bead, but that's the exaggeration of the way I've drawn the PowerPoint slide. The weld bead isn't as big as that. The weld bead is just a couple of millimeters. So don't think it looks like that. Okay? And the advantage of this process is very, very simple. And the principle for design purposes, that you can rely on is that the strength of a welded pipe, the strength of the weld is always greater than the strength of the pipe body. You never want to be in a situation with plastic pipes, you never want to be in a situation where the joint is weaker than the pipe. You usually work on the principle that you design the joint to be stronger than the pipe. So you only have to design that, if you can count on that, then you only have to design the pipe. You don't have to worry about the joint. And the main reason why the joint in a butt welded pipe is stronger is because you've produced this bead on the pipe, so you've effectively thickened up the section. But I say, don't run away with the idea of thinking that the bead is very large. It's not as large as I've drawn it there. So, weld beads, they're usually left on the inside and outside of the pipe. You can remove them if they want. Local thickening ensures that the weld is stronger than the pipe. Beads may be shaved off if necessary, but this is not usually done because it's not good for the strength of the pipe. So, just once again, I like doing this. Took ages making these. Right, so there's the machine pushed up against the hot plate. Hot plates removed, pipes butted up against one another, and there's your welded joint. Completely without human interference, so all controlled by the box which controls the machine. So that's butt fusion. I mentioned electrofusion. With electrofusion you have fittings, you have socket fittings, but on the inside of each fitting you have a metal coil. These fittings are actually made, I've not talked about the process of injection moulding. The two main processes for thermoplastics are extrusion, which I've shown you, and injection moulding, which is just like extrusion, except you push it into a mould. So these fittings, electrofusion fittings, are made using a mould, and on the inside of the mould, of course, you have to wrap these electrical conductors. So I'll bring one of them along next time. I'll show you an electrofusion fitting, but basically it's just a straight, simple socket fitting, but with a conducting coil wound around the inside of the fitting. So electrofusion involves injection molded fittings with an electrical heating element molded into the inner surface. So here's the electrofusion process, and again it's completely automated so that you don't have a chance to, the operator doesn't have a chance to mess it up. So you insert the pipe ends, you clean up the pipe ends in exactly the same way as you would for butt fusion, and then you insert the pipe ends into the fitting body, and then you press the button on the controller and it passes the correct current for the correct amount of time. So the heating element melts all the material around it, and then the joint is allowed to cool. And actually this controller, the way they do it mostly, see here's one example of an electrofusion coupler, and here are the places where you plug in the two electrical electrodes for heating. And actually there's a coding system, because the controller knows what type of fitting is going to be used. So it'll know the diameter of the fitting, and it knows this from the distance apart of the two electrodes. So you just connect the two electrodes to the electrofusion fitting, and that tells the controller reads the distance apart between the two electrodes, and that tells the controller what sort of fitting it is. So it knows what current to pass and for how long a time. So that's electrofusion fittings. That's just a straight coupler, but electrofusion is used for unequal couplers, it's used for elbows, it's used for T's. It's very, very widely used. Of course, the disadvantage of electrofusion is that it's very expensive. Having this additional socket with the electrodes on the end, with the wires on the inside, is much more expensive than a butt weld. So, given the opportunity, you prefer to do a butt weld, but in many in many applications, because of reasons of space, or because you might be joining pipes of different diameter or something like that, you have to go to electrofusion. So that's the electrofusion joint. So, I think I'm fairly near the end of this. Yeah. Just some applications of thermoplastic pipes that you'll come across. Of course, thermoplastic pipe is used for transmission of water or gas in domestic, in cities. And the usual code, I think most places in Europe, the usual code is if it's water, it's blue, and if it's gas, it's yellow. So that's what all the yellow stuff is. But it's also used as a liner. I mentioned these thermoplastics can be used as a liner for steel tubing, both as new build and also rehabilitation. If you've got an offshore flow line and it's beginning to corrode a lot because you're transmitting possibly injection water, which is very corrosive, you get a corrosion problem, you can actually subsequently draw into the inside of the pipe a line, a plastic line. You can actually use these as a method for rehabilitation of steel pipe. So I'll talk about that, rehabilitation, and there are also liners for high pressure flexible hoses. I'll talk about that to some extent as well. This is how you do lining, which I'm going to have to knock off in a second so I can get the next. This is called swage lining. So here's your pipe. You take it through a roller box, and the roller box rolls it down and reduces the diameter of the plastic pipe, and then you draw it into the steel pipe, and then when you've let go of it, it reverts, because these materials are viscoelastic. So you squash it, a few seconds later it will swell back up. So this is called swage lining. This is probably the most common method used for rehabilitating steel pipes, because you get a tightly gripping liner. The other is called slip lining, where you just have a liner which is a loose fit, and you just pull it into the pipe. And the other thing you can do is you can have a deformable liner. You'll get your thermoplastic liner. You make it as a tube. You squash it and tie it up with little bands. So you fold it up, and then you pull it into the pipe. And then when you pressurize the liner, all the places where you've tied it up, the ties break. The ties are just like the ties are used for electrical wires. They just break, the thing expands, and it fills the pipe. Right, I better stop now, otherwise we're going to be late for the next lecture. You have a next lecture. So I'll see you here. Just have a look through what I've done there. Have a look through the notes. Look through textbooks on plastics if you want to. Hopefully, for my part of the course, most of the stuff that you need will be in my lecture notes. And I'll see you 2 weeks then. Okay? So if you come along here next time, you'll remember. He always said he wasn't going to do it. So sit down and look through lecture notes.
I don't know how maybe it's just to say, oh, we have
Injection molding.
Yeah, unfortunately, usually I'm not going to be here next time. So, I don't know what to suggest. Not as well as Newcastle, no.
So this
Try,
is
try, who's the postmaster for this? Is it Julia? It's football.